Good morning. Let's continue with the Hamming codes. In the last class, we have started Hamming codes. We'll continue. Now, what is Hamming code? Hamming code is error detection and error correction code, right? Error detection and error correction code. How many errors it will detect and correct? Only single bit errors. And there is much probability that only error occurs in single bit, not in many bits. So we are much interested in correcting single bit errors, and Hamming code is one such code. And what is how we form Hamming codes? There are two parts. We construct Hamming codes and we send from the transmitter. This construction part is done at the transmitting end. Detection part is done at the receiving end. Now let's see how we construct the Hamming codes. And it is divided into three steps. In the first step, we have to find the number of bits, parity bits, to be added to the actual message bits. And here we say M be the number of message bits that are transmitted from transmitter to the receiver. And this is not N, this is P. P be the number of parity bits that are required for error correction. Let P be the number of parity bits that are required for error correction. That P can be found, that P is found by using this relationship. 2 power P greater than or equal to M plus P plus 1. And in the last class we have seen, if there are 4 message bits, P found to be 3. If there are 4 message bits, P found to be 3. Means you need 3 parity bits. You need 3 parity bits, and there are 4 message bits. Totally, Hamming code will have 7. How many bits? Totally, there will be in the Hamming code 7. And out of 7, 4 are message bits, 3 are parity bits. That's why we get totally 7 bits in the Hamming code, right? That is the first step. In the step 2, what we do? In the step 2, how we place the parity bits along with the message bits? Are they placed at the beginning of the message bits, or at the end of the message bits, or in the middle? We insert parity bits at different places. The answer is we place the parity bits at different places, at chosen places. And what are the chosen places? Let's say there are 7 bits in the Hamming code: bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. And in what places we insert these parity bits? At these places. In the places whose number is in terms of 2 power 0, ascending powers of 2. Ascending powers of 2 means in the bit 1 place. Bit 1 place is nothing but 2 power 0. Bit 2 place is nothing but 2 power 1. And what is 2 power 2? 4. So in bit 1, bit 2 and bit 4, first place, second place, fourth place, we insert the parity bits. And we have 3 parity bits for 4 message bits. So P1 comes here, P2 comes here, P3 comes in bit 4 position, not in 3, in bit 4 position. So we have all the parity bits inserted. There are only 3 parity bits for 4 message bits. So after inserting parity bits P1, P2, P3 in the places, in the positions 1, 2 and 4 respectively, the remaining places, which is bit 3, bit 5, bit 6 and bit 7, are filled with message bits. So M1 comes here, M2 takes the position of bit 5, M3 is in bit 6 position, M4 is in 7th place. Okay, like that we place the parity bits in the chosen places. That is step 2, right? In the step 2, we place the parity bits And now step 3 is about finding out those parity bits. Okay, parity bits means now we have not yet found them. We have given only places for the parity bits. Next step is to give values to those parity bits. Those parity bits are the 1 or 0. Values means here parity bit is a binary number. It can be either 0 or 1. Now let's see. Now step 3 is assignment of parity bit values, either 1 or 0. That assignment involves the following steps. See, first for that we make a table like this. Having 1, 2, 3, 4, 5 rows. The first row is given the name bit designation. Second row is given the label bit position. Third row is given the label binary position number. Fourth row is given the label information bits. Fifth row is given the label parity bits. So bit position, let's say there are 7 bits in the Hamming code. Write down, give numbers to those bit places, starting with the left one. This is the first bit, second bit, third one, fourth, fifth, sixth, and seventh. And just now we saw the parity positions. So in the first place we have P1, second P2, third one is M1 message bit, fourth place is again parity bit, and remaining places 5, 6, 7 will have message bits. And binary bit position, what is the position of this bit? First bit. So there are 7 bits, you need only 3 bits to represent that in binary, and that is this is 001 is just representation of 1, position 1 here. Okay, 010 is nothing but the binary position number. It is position which is represented not in decimal but in binary. Okay, like this. On information bits, the bits that you want to transmit are written in this row, parity bits. Once we have information bits, we can find out parity bits based on the following. Okay, based on the following. On this Hamming code construction, it may use either even parity or odd parity. It may use either even parity or odd parity. Now let's see. Now information bits are known. This is given. Okay, and what we have to find out is parity bits. So P1, P2, P3 are unknown bits, whereas M1, M2, M3, M4 are given bits. You know what bits are to be transmitted. You don't know P1, P2, P3. These bits are to be known based on M1, M2, M3, M4 and which parity you are using at the transmitting end. Is it even parity and also odd parity? So, and finding out the value for P1 is based on the following. This parity bit P1, okay, this parity bit P1 checks what bit positions. See, P1 is having 1 in the rightmost place, in the first bit place. P1 is having 1 in the first bit place. So this P1 checks the bit positions 1, this one, and bit place 3 is also having 1. So 3 also, and fifth bit is also having 1 in the first place. This is the first place. So bit 2 is not having, bit 3 is having, bit 4 is not having, bit 5 is having, bit 6 is not having, bit 7 is having. So parity bit P1 checks all the bit positions which is having the first bit as 1. So parity bit P1 checks first bit, third bit, fifth bit and seventh bit. So parity P1 checks 1, 3, 5 and 7. In the same way, parity P2 checks which bit positions. Parity bit P2 is having 1 in the second place. In the second place when you move from right to left. So find out the places where 1 is lying in the second place. So parity bit P2 checks bit place 2, bit place 3 also, because it is having 1 in the second place, not bit 4. Bit 4 not bit 5, bit 6 and also bit 7. So parity bit P2 checks these bit positions 2, 3, 6 and 7. That's what parity bit P2 checks. Next, P3, coming to the parity P3 checks, see in which place the parity P3 is having 1, in the third place, in the last place, or in the first place when you move from left to right, in the leftmost place, right? So here it is 0, here it is 0, here it is 0. So it is having 1, fifth place also, sixth place also, seventh place also. In all these places, 4, 5, 6, 7 place, there is 1 in the leftmost place, right? So P3 checks the bit positions 4, 5, 6, 7, right? So that's what we said here. So P1 checks bit positions 1, 3, 5, 7. You don't need to by heart these numbers. Okay. Now just now we found some logic. You remember that logic. You can frame these numbers. You don't by heart these numbers. If you by heart, you may not remember correctly. So avoid by hearting. Just try to understand that logic. P1 checks bit positions 1, 3, 5, 7, whereas P2 checks bit positions 2, 3, 6, 7. P3 checks bit positions 4, 5, 6, 7. So based on this bit positions only, P2 will get either 1 or 0. Okay. P1 will get either 1 or 0 based on these positions. What positions? Bit positions 1, 3, 5, 7. In the same way, P2 will get either 1 or 0 based on the bit positions 2, 3, 6, 7. Okay. P2 is in the place 2. So based on what is already have in the places 3, 6 and 7, based on these three positions, bit P2 will get either 1 or 0. In the same way, P3 will get value 1 or 0 based on the place 5, 6 and 7. They are message bits. So based on what message bits are in these places 5, 6 and 7, based on that 4 will get either 1 or 0. And also we have to consider, is it even parity or odd parity. So this is what Hamming code construction is. Now let's understand one example. Let's understand Hamming code with this example. The first example is determine the single error correcting code for the BCD number. What is the BCD number given? 1001. And he is saying it is information bits using even parity. Okay. At the transmitting end, how many bits are transmitted? 1001. This many bits are transmitted. There are 4 bits, and transmitting circuit is using even parity in the construction. Okay. So transmitting circuit is using even parity for constructing the Hamming code. Okay. So now we have to construct Hamming code. This is the given information bits or message bits. This is M1, M2, M3, M4, and we have to add parity bits, right? We have to add parity bits. For 4 message bits, how many parity bits are needed? 3 parity bits. That is found in the step 1. Step 1 is find the number of parity bits required. Okay, right? Number of parity bits required. And we have to consider this equation. What equation? 2 power p greater than or equal to m plus p plus 1. You have to choose value for p so that that relationship is satisfied. 2 power p greater than or equal to m plus p plus 1. And we have already found it, and its value is 3. So there will be 3 parity bits and 4 message bits. So totally Hamming code will have 7 binary digits, 7 bits. Next, second step is to construct the bit position table. Okay, second step is to construct the bit position table. This is the bit position table, right? And bit position table, just give numbers here. Starting from the leftmost bit, you proceed towards right. So 1, 2, 3, 4, 5, 6, 7. You write the same thing in binary. We called it binary position number 001. This place has the binary position 001. This place 2 is having the binary position, binary value 010, like that. And in the second step, what we do is we assign places to the parity bits according to what? Ascending powers of 2 means starting with 2 power 0. 2 power 0 is 1, 2 power 1 is 2, 2 power 3 is 2 power 2 is 4. So in these places we have parity bits, in remaining places we have message bits, right? Next, information bits. Write down the information bits. What is the information bit? It is given in the question itself. 1 0 0 1. So first one goes in which place? M1. M1 is bit 3 place. Second bit 0 comes in M2, which is 5th place. Next one is 6th place, which is M3. Next bit is M4 bit, which is in 7th place. Okay. Now in the third step, determine the parity bits as follows. In the second step, we assign positions to the parity bits. In the step 3, we find out the values for parity bits. So what are the, in the construction, in the Hamming code, we know there will be 7 bits. Out of 7 bits, 4 bits are known. They are information bits. They are given in the problem itself. And how many bits are yet to know? 3 bits. Okay, what are those 3 bits? P1, P2, P1 is pending, P2 is pending, P3 is pending. So that we will do now. Okay, now what is P1? And the problem also saying use even parity. So even parity means, so P1 checks which bit positions 1357, right? 1357. 1 is not yet found. We have to find it now. Okay. 3. Where is 3? This is 3. 3, 5, 3, 1, 3, 5, 7. 7. And we have to use even parity. 7 is having 1. 5 is having 0. 3 is having 1. So you have to write something here. So that these bit places 1, 3, 5, 7 will have total number of ones even. Will have total number of ones as even. Okay. Now there are how many ones? 3, 5, 7 is having 1. There are 2 ones already. Now you cannot change those numbers. You cannot change those numbers. Now we have to adjust P1 so that there will be totally even number of ones. In what places? In what group? Group containing bit positions 1, 3, 5 and 7. So we already have 2 number of ones. So we have to write 0 here. If I write 1, what it becomes? There will be 3 number of ones. That becomes odd parity. And we have to follow even parity for this problem. So writing 0 makes this group of bits 1, 3, 5, 7 a even parity. In the same way, we find out the bit P2. We find out the bit P2. Is it even? Is it 1 or 0? Now bit P2 checks which bit positions 2, 3, 6, 7. Now let's say 2, that we have to find out. 3, 6, 7. 3, this is 3, this is 6, this is 7. 3 is having 1, 6 is having 0, 7 is having 1. They are already having 2 number of ones. Okay, so we have to write 0 to make it even parity. Okay, even parity means bit 2, what value is to be given to bit P2 means bit 2, so that the group 2, 3, 6, 7 will have even parity. Even parity means the total number of ones present in the group 3, 6, 7 including 2, including the position 2 is even. So if I write 0, then 0, 1, 0, 1. So here we have 0, 1, 0, 1. Totally we have 2 number of ones which is even. If I write 1, then it becomes odd parity. We have to follow the even parity for this problem, right? For this problem. Next. And in the similarly you can find out bit P3. Okay, bit P3 checks 4, 5, 6, 7. 4, 5, 6, 7. 4 is parity bit that we have to find out. 5, 6, 7. 5 is 0, 6 is 0, 7 is 1. So we have only one number of 1. To make it even, we have to give 1 to the parity bit 3, P3, which is in bit place 4. So P3 becomes 1. So finally what will be the Hamming code? 0, 0, 1, 1, 0, 0, 1. So the resulting Hamming code is 0, 0, 1, 1, 0, 0, 1. So this is the construction of Hamming code. Later we will see the decoding. Okay, how this if there is any error in the Hamming code which is transmitting at the transmitter side, this code may not receive correctly at the receiver side. It may be received correctly or it may not be received correctly. How the receiver detects the error if there is any error at the receiving end? Error may be caused by channel noise or maybe other reasons. Next, another example. In this example also we construct the Hamming code. Now let's do this example. Determine the single error correcting code. Single error correcting code means Hamming code only. For the information code, what is information code? 10110. This is the message 10110 for odd parity. Now in the example 2, he is asking us to use odd parity. In the previous example, he asked us to use even parity. Here we have to use which parity? Odd parity. And what is the information? 10110. This is a message. M1, M2, M3, M4, M5. How many message bits are there? 5 message bits. It is not 4. There are 5 message bits. Now let's see how to construct the Hamming code for 5 message bits. What is the first step? We have to find out number of parity bits that are needed to be added to construct the Hamming code. Now that number varies, number of parity bits required, that number varies according to the number of message bits. This time we have message bits to be 5. So M equal to 5 and calculate this M plus P plus 1. M is 5, let P be 4. Let P be 4. 5 plus 4 plus 1 is 10. So other side of the relationship here, M plus P plus 1 is 10. Now P equal to 4. 2 power 4 is what? 16. 16 is greater than or equal to 10. So P is the value which satisfies, P equal to 4 satisfies this relationship, right? So P equal to 4 is the required number of parity bits. So there are 5 message bits and there will be 4 parity bits. Totally our Hamming code will have how many number of bits? 5 plus 4, which is 9. So our Hamming code will have 9 number of bits. Out of 9, 4 are parity bits, remaining 5 are actual message bits, right? Actual message bits. Next. So once we found the number of parity bits required, next step is to construct the table, bit position table, and give correct places for the parity bits. So second step, we construct the what? We construct the table like this, bit position table. This is called bit position table. And in this bit position table, we assign correct places for the parity bits. So which places will parity bits get? The places which are ascending powers of 2, starting with 2 power 0. 2 power 0 is 1, 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8. So 1, 2, 4, 8. In these places we place the parity bit. In the remaining places we put the message bit. So P1 comes in place 1, P2 in place 2, P3 in place 4, P4 in place 8, bit position 8. Okay, remaining places 3 is for M1, M2 comes in bit place 5, M3 in place 6, M4 in position 7, M5 in position 8, right? After constructing this bit position table and also fill this row with binary position, binary equivalent of this decimal, okay? And how many bits are there in this example? In the Hamming code construction, totally there are 9 bits. So to represent 9 bits, we need 4 binary digits, 4 places, right? 4 binary digits. That's why we have this representation 0001, 0010 for 3, 0011 for 6, 0110 for 9, 1001. Next, fill this row with information bits. What is the information bit given? This is given in the problem. So M1 is 1, M2 is 0, M3 is 1, M4 is 1, M5 is 0. These are the knowns. And what are the unknowns? P1 is unknown, P2 is also unknown, P3 is also unknown, P4 is also unknown. These parity bits are to be found based on the message bits and also which parity we are using. Is it even parity or odd parity? So we are using odd parity here. So we use these things, right? Let's see how we find out. Now P1 checks which bit positions. P1 checks which bit positions. 1, 3, 5, 7 and 9. 1, 3, 5, 7 and 9. Why 1, 3, 1, 3, 5, 7, 9? P1 is having 1 in the first bit place. P1 is having 1 in the first bit place. So it checks the bit positions where first bit is 1. Okay, it checks all the bit positions whose first bit is 1. Okay, P1 checks all the bit positions whose first bit is 1. Okay, in this place the first bit is 1. In the third place also first bit is 1. Fifth place also third bit is 1. Not 6, yes, 7 and 9. So P1 checks first, third, 5, 7, 9. So that's what we have written here. 1, 3, 5, 7, 9. So P1 checks all these places. Now which parity is to be used? Odd parity. So 1, 3 is having 1 already. 3, 5, 0, 7, 1, 9. Now consider this one. 3, 5, 7, 9. 3, 5, 7. So 1, 0, 1, 0. There are how many number of ones? 2 number of ones. There are how many number of ones? 2 number of ones. So to make it odd, we are using odd parity. To make it odd, we have to add 1 here. So in the P1 gets 1. P1 gets 1. So 1. If you write P1 1, then this group 2, 3, 6, 7, the group containing bit positions 2, 3, 6, 7 will have a odd parity, not otherwise. In the same way, not this one, not 2, 3, 6, 7, 1, 3, 5, 7, 9. Okay. So in this place, in the first place, we have written 1, so that this bit positions 1, 3, 5, 7, 9, this group will have odd parity. Okay. Next, P2 checks which bit positions 2, 3, 6, 7, right? P2 is having 1 in the second place. So it checks all the bit places whose second bit is 1. So this one and this one and this one, that's all. 2, 3, 6 and 7. 2, 3, 6, 7. So 3, 6, 7 are message bits. 3, 6, 7. They're having how many? 3, 6, 7. All of them are ones. So the ones means there are 3 ones. Now we have to assign. You have to give something here. You have to write something here based on these ones. There are 3 ones already, means odd number. So if you write 1 again, then it becomes even parity. So we have to write 0. So we have to write 0 here to keep that even parity. Sorry, odd parity. So we have to write 1. We have to write 0 to keep that odd parity. So we get 0 here. In the same way, P3 checks which bit positions? 4, 5, 6, 7. 4, 5, 6, 7. So why 4, 5, 6, 7? P3 is having 1 in the second place from right side. So P3 is having 1 in the second place from the right side or left side? From the left side. Okay, from the left side. So identify the bit places whose second place from the left side is 1. Not this one, not this one, not this one, of course this one. Here 5, this one, 6 also, 7 also, not 8, not 9. So P3 parity checks bit places 4, 5, 6, 7. So fourth bit is parity bit. Now we have to decide what we have to decide value for fourth place based on the values which are already present in 5, 6 and 7th place. 5, 6, 7 places are message bit places. So see what is there in 5th place, 6th place and 7th place. 5th place is having 0, 6th one is 1, 7th one is 1. So there are two number of ones which is even, and our intention is to make it odd parity. So we write 1 here. If we write 1, then 1, 0, 1, 1, there will be 3 number of ones which is odd parity. So by writing 1, by giving value 1 to P3 makes the group containing positions, bit positions 4, 5, 6, 7 and odd parity. Okay. Next. Now what is there is another parity bit P4. So let's see what P4, how P4 got 1 here. Okay. P4 checks the bit position 8 and 9 only 8 and 9. Why? Look at P4, its binary equivalent is 1, 0, 0, 0. P4 bit is 8th position. Its binary number is 1, 0, 0, 0. 1 is in the first bit from the left. Now identify the bit positions whose first bit from the left is 1. Not this one, 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 not this, not this. 8th place is having bit position 1. 9th place also. So it checks only bit positions 8 and 9. Parity P4 checks bit positions 8 and 9. Right? Now odd parity. We are looking for odd parity. So 9th place is having 0. It is we have 0. Number of ones is 0. Means it is even parity. So we have to add. We have to write 1 here. So we have, if I write 1, then bit place 8 and 9. This group having bit places 8 and 9 will have how many number of ones? Total number of ones will be 1 if I write 1 here, which is odd. So we have to write 1 here. If I write 0, then 0 here, 0 here. So what happens? 0 here, 0 here, it becomes even parity, right? So P4 gets 1 like that. So there is the resultant code will be, now write down all the bits in this order. 1, 0, 1, 1, 0, 1, 1, 1, 0. So the resultant combined code is 1, 0, 1, 1, 0, 1, 1, 1, 0. Count number of bits present here. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 bits. Out of these 9 bits, 5 are message bits and 4 are parity bits. Okay, parity bits. Let's continue. The next topic, it is continuation of Hamming codes. Right. So for what we have done, what we have seen is how to construct the Hamming code. How to construct the Hamming code. This construction takes place at the transmitting end. Okay, transmitting end. Now the constructed Hamming code is transmitted. If there will be any error, if there is any error, single bit error, okay, certainly if there is a single bit error, certainly the code what is transmitted will not be received as it is, and now here what we will see is how receiver with the correct circuit, okay, how the receiver detects the error, how the receiver detects and corrects the error. Now what we are seeing is how Hamming code is used to detect and correct the error at the receiving end. Okay. Right. See this, you can read these lines. Let's do it in steps. Step 1, these are the steps which are done at the receiving end, at the receiving end. So start with the group checked by P1. We have already have seen at the transmitting end what are the bits checked by P1. P1 checks, start with the group checked by P1 means check the group for proper parity. Okay, check the group for proper parity. A 0 represents a good parity check and 1 represent a bad parity check. See, we have to apply this parity checking. Okay, now how many parity bits are there? There are, let's say there are 3 parity bits. We have to check this parity. Okay, each for 1 parity bit. Now if parity is good, either even parity or odd parity, then that parity check yields a value. If it is a good parity, it yields a 0. If it is a bad parity, then it yields a bad check. If it is a bad parity, then it produces 1. It produces 1. If it is a good parity, it produces 0. We will see what it is. Okay, and in this, that is step 2. Step 3, repeat step 2 for each parity group. Means we have to do the same process for all the parity. How many parities are there? That many times we have to repeat that step 2. Okay, in step 4, see, we have to form, we will form the number, the binary number formed by the result of all the parity checks. The binary number formed by the result of all the parity checks designates the position of the code bit that is in error. Means by forming number that results out of this parity checks. How? If it is a good parity, it we write 1. Sorry, we write 0. If it is a bad parity, we write 1. Based on that, we form one number. That number tells us which bit position is in error. Okay, if all the parity checks use zeros, means if all the parity checks are very good, okay, good, then the received code is correct, otherwise it is not correct. And which bit position is in error, how we get to know? We have to form one number based on the bits that results after performing the parity on all these groups, right? Now let's see what are the steps. You may not understand like this if you read. If you look at one example, then it will be clear to you. Okay, let's do some examples. Let's say example, the received code is, this is the received code 0010001. Count how many number of bits present in the received code. 1 2 3 4 5 6 7. There are 7 bits in the received code. 1 2 3 4 5 6 7. 7 is the received code, means you can guess how many number of information bits. Out of 7, how many are the actual message bits and how many are the parity bits? So 4 are parity bits, sorry, 4 are message bits and 3 are parity bits. And we also know which are the message bits, which are the parity bits. First place, second place, and this fourth place are parity bits. Other places are message bits, right? Continue. Designate any error that has occurred in transmission if even parity is used. So what parity is used? Okay, even parity is used, means both transmitter and receiver are using the same parity. They should use same parity, otherwise it doesn't work. Both transmitter and receiver should use the same parity. There are 4 message bits and 3 parity bits. Of course it is so. Now it is the solution. Let's see how we correct the bit if there is any bit in the error. If there is any bit in error. Now first make a bit position table. Okay, write down a bit position table like this, just how we have done it in the transmitting end. Okay, see, bit designation means bit position. There are seven Hamming code bits. So write down 1 2 3 4 5 6 7 and write down these places. First bit is parity bit, second bit is also parity bit, third bit is M1, fourth bit is parity bit again, fifth, sixth and 7 are M2, M3, M4 respectively, right? And for the information, for easy decoding, you also write down the bit position number. And there are 7 bits. You need only 3 binary bits to represent all these 7. So 001 for 1, 010 for 2, 011 for 3, and so on, right? And received code, write down the received code also. This is also known, 0010001. This is the received code. Write this as it is, starting from the left bit, proceed towards the right. Next thing is, now see, how many parity bits are there? There are 3 parity bits, P1, P2, P3. So we have to perform parity check 3 times, each for 1 parity. So we have to perform parity check 3 times on different group of bit positions. So first parity check, this is the first parity check. Bit P1 checks which positions, 1 3 5 7, right? This we know why, how. Okay, bit P1 checks positions, which positions, 1 3 5 7. First position, third position, fifth position, 7th position. For easy, to avoid confusion, I have written this 1 3 5 7 position bits here. Okay, first position we have 0, this is that 0. Third place we have 1, this is that 1. And in the 5th place we have 0, that is this 0. And in the 7th place we have 1, that is this 1. Bit P1 checks positions 1 3 5 7 and just write down these bits beside, so that you can calculate number of ones present in this place, in these positions. How many ones are there in these positions? There are 2 ones. And this problem is used if even parity is used, means we at the transmitting end even parity is used. So how many number of ones here? There are 2 number of ones, which is even or not? Yes, there are 2. There are 2 ones in this group, which is even parity, right? So parity is correct or not? Parity check is good. Parity check is good. Okay, 0, write down 0 here. Parity check good. If parity check is good, then you have to write 0 and call this as LSB number. Okay, call this as LSB number. Next, and go for the next parity, P2, second parity check. Bit P2 checks which bit positions? Bit P2 checks which bit positions? 2 3 6 and 7, and write in brackets which is in, what is there in bit place 2? 0 in the received code, 0. 3 in bit place 3, what is the received code? 1, that is this one. 6, this is the 6. 0, and what is there in 7? This is the 7th place, 1. Okay, 0 1 0 1. How many number of ones there are there in this group, which is checked by the parity P2? There are 2 number of ones. 2 is even, so there are 2 ones in this group, which is even parity, right? So parity check is good or bad? It is good, right? If it is good, then we have to write 0. Parity check good yields 0, parity check bad yields 1. Okay, write down. Next one, third parity check. Okay, the third parity check, bit P3 checks positions. What positions? 4 5 6 7. 4. What is there in bit place 4? This is 4, 0. Okay, 4, 5, 0. 6 also 0. 7, 1. 0, 0, 0, 1. Right? So there are 1, 1 in this group. Is it even or odd? How many number of ones are there? There is only one number of 1, which is odd. Parity. We want even parity, but what we got here is odd parity. So parity check is bad. If parity check is bad, it is 1. We have to write 1. And this is since P3 is the last parity bit, right? Last parity bit, write on 1 here, and that ends. Okay, and we don't need to, there is no parity bit for doing the same thing again. Okay, this is the last check, parity check. Okay, and 1. Now form one number like this. This is the LSB bit which we got after in the first parity check. How we got this 0 here? If parity is good, we write 0. If parity is bad, we write 1. The first, this 0, which we got after checking the first parity, first group, and that comes here. Next, second parity check, that is the return value that is to be written here on the last one. Okay, which is the MSB bit, right on here. If you form number with the results that we got after the parity check is being done, and form the number. Now what is the number? 100. What is its equivalent decimal? 4. So binary, what it is saying is binary 4 means bit 4 is in error. What is the bit 4? This is the 1, 2, 3. Bit 4 is in error. Means it is in error means what is received is not correct. Now what we have received is 0. What should be the correct value? What should be the correct value? Here 1. So the correct code should be 001, not 01, 001 1 001. That's the answer. So the correct code is 001 1 001. Remaining places won't change. All bit places are received correctly except the fourth bit. Instead of receiving 1, it received 0. Okay, it received 0. 0011001. So the correct code is 0011001. Don't change the other bits, change the bit which is in error. So this formed number is saying fourth bit is in error. Error means the received bit is not correct. So if 0 is not correct, what is the other possibility? 1. So 0011, remaining bits 001. All other bits won't change, only the bit which is in error will be complemented or inverted, and that is the received code. This is one example. Let's do another example. The code 10111010 is received. This is the received code. The correct any errors. Correct any errors. There are 4 parity bits and odd parity is used. Odd parity is used. He is saying odd parity is used. Count the number of bits which are received. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 bits received, and he is saying 4 parity bits. Okay. Out of 9 bits, 4 are parity bits, and remaining 5 are message bits. Right. So on this received, the bit, the transmitter side, what parity is used? Odd parity is used. Okay. So let's make the table like this. Bit position, since there are 9 bits, write down the numbers like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the first bit, second bit, and so on. This is the last bit. And for 9 bits, how many, if there are totally 9 bits in the code, how many parity bits will be there? 4 parity bits, right? What are those places? Ascending powers of 2 power 0, 1. 2 power 1, 2, 2 power 2, 4, 2 power 3, 8. So 1, 2, 1, 2, 4, 8. These places parity bits are positioned, right? So P1 is sitting in first place, P2 is sitting in second place, P3 is in fourth place, P4 is in eighth place. 1, 2, 4, 8 are parity bits. And what are the message bits? What are the message bits that are actually useful? 3, 5, 6, 7, and 9. These are the bit positions in which message bits are placed. Okay. Next, write down the binary position number. Since there are nine places, 9 bits, we have to use 4 bits. If you use only 3 bits for binary, fine, then you can represent only 7 bits. So there are 9, we have to use 4 bits. What is the binary equivalent? For 1, 0, 0, 0, 1, for 2, 0, 0, 1, 0, and for 7, 0, 1, 1, 1, for 9, 1, 0, 0, 1, right? And received code, write on the received code also, write this as it is, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0. Now what we do? The same thing. First parity check. P1 checks which bit positions. Bit P1 checks which bit positions. 1, 3, 5, 7, 9. You know why? How? Okay. 1, 3, 5, 7, 9. Collect. Just write down the bits which are present in these places. 1, 3, 5, 7, 9. 1. We have received 1. Write down this one here. In the third place, we have received 1. Write down this one here. In the fifth place, we have received 0. Write down this 0 here. In the seventh place, we have received 0. Write down this 0 here. And this 9, 0, this is that 9. Okay, ninth place is 0. Okay. Now at the transmitting end, what type of parity is used? Odd parity. Now we have to look for odd parity, not for even parity. So how many number of ones? Odd parity means the number of ones present in the received code should be odd. Okay, how many number of ones here? There are 2 number of ones. Is it 2 odd? No, there are 2 number of ones in this group. Now is it odd parity? No, right? Parity check is bad. If it is bad, what should be written? 1, and that becomes the LSB. First parity check is number which is the LSB of the resultant number. Okay. Second parity means bit P2 checks which bit positions? 2, 3, 6, 7. Okay. 2, 3, 6, 7. Write down the bits received in these places. 2, 3, 6, 7. 2, 3, 6, and 7. Okay. 0, 1, 1, 0. Here also we have how many number of ones? 2 number of ones. There are 2 ones in this group. It is again even parity, but what is with what parity the transmitter sends the data? Odd parity. So we received even parity here. Parity check is bad again. So we have 1 here. We write 1, right? Next, third parity check. Parity P3 checks which positions? 4, 5, 6, 7. Okay. 4, 5, 6, 7. 4, 5, 6, 7. 1, 0, 1, 0. That's what we have written here. 1, 0, 1, 0. So again, this is bad parity. Okay. There are 2 ones in this group. Parity check is bad. If parity check is bad, we write 1. Okay. Now, fourth parity also we have to do, because there is P4 also. Bit P4 checks positions 8 and 9. Okay. 8 and 9. Let's see what is there in 8 and 9. This is 8. This is 9. 1, 0. Okay. This is 1, 0. 1, 0. Now let's see, there are how many number of ones? There is 1 number of 1, which is odd number of ones, right? There is 1, 1 in this group. So parity check is good. If it is good, we have to write 0. And since this is the last parity check, this becomes the MSB bit. Now form the number with the results that we got in the parity checks, right? So this is the MSB bit that comes here. Next one is the next MSB. This one. So what we get? 0, 1, 1, 1. This is the LSB. Next bit. This is the MSB. So 1, 1, 1, 0. So this formed number tells the place tells the binary position which is in error. Now what is the equivalent? 0 1 1 1 means what? 0 1 1 1 means 0 1 1 1 is 7th place. 7th place is in error. So what is received is 0. What should be received correctly is 1. Okay, if there is no error in the channel, then this instead of receiving 0, we would have received 1. So the correct code is 1 0. Remaining places are received correctly. Only 7th place is received incorrectly. So the corrected code is 1 0 1 1 0 1, not 0. It becomes 1 now after correction. 1 0. These two remains same. So 1 0 1 1 0 1 1 1 0. That is the corrected code. Like this we can use Hamming codes for error detection and also correction. This ends with Hamming codes.